File deletion in HDFS begins when a user executes the HDFS dfs rm command to remove a file or directory. Upon deletion, the file is not immediately erased but moved to a designated trash directory located at /user//trash/current, provided the trash mechanism is enabled. The file remains here temporarily, acting as a safety net against accidental deletion. After a configurable interval defaulting to 6 IRs but adjustable via the fs.trash.interval parameter, the file is permanently purged. During this final deletion phase, the name node removes the file's metadata from the namespace, and the associated data blocks on data nodes are marked for deletion. These blocks are asynchronously removed during subsequent data node heartbeats to the name node, ensuring efficient resource management without immediate overhead. The trash mechanism serves as a critical safety feature, preventing irreversible data loss by temporarily retaining deleted files. It is enabled when fs.trash.interval is set to a positive value e.g. 0. To restore a file from trash, users can manually move it back to its original path using HDFS dfs mv-trash path original path. However, if immediate deletion is necessary, bypassing trash, users can append the skipTrash flag to the rm command e.g. HDFS dfs rm skipTrash. This action irreversibly unlinks the file's data blocks instantly, making recovery impossible. This approach is typically reserved for ephemeral or non-critical data where rapid storage reclamation is prioritized over safety. Internally, HDFS handles file deletion through coordinated actions between the name node and data nodes. When a deletion command is issued, the name node immediately updates the file system metadata to reflect the removal, eliminating references to the file from the namespace. The actual data blocks on data nodes, however, are not deleted synchronously. Instead, data nodes lazily remove these blocks during their periodic heartbeats to the name node. This asynchronous cleanup minimizes performance bottlenecks, as data nodes process block deletions in the background while prioritizing active read/write operations. The process ensures metadata consistency while optimizing cluster resource utilization. HDFS snapshots provide point-in-time, read-only copies of directories or entire file systems, enabling data recovery and versioning without duplicating blocks. They operate on a zero-copy principle. When a snapshot is created, it captures only the state of the directory at that moment. Subsequent modifications to files or directories trigger a copy-on-write TOW mechanism, where changed blocks are duplicated while unchanged blocks remain shared. This design minimizes storage overhead, as snapshots store only incremental deltas changes rather than full copies. Consequently, snapshots are highly space-efficient and ideal for preserving historical data states. Snapshots offer 3 key benefits: recovery from accidental deletions/corruptions, backup for point-in-time restores, and auditing of historical data changes. To utilize snapshots, administrators first enable the feature on a target directory using HDFS dfsadmin allow snapshot/path. Once enabled, a snapshot e.g. phone is created via HDFS dfs create snapshot/path phone. When files in the snapshotted directory are modified, HDFS employs copy-on-write. The original block is preserved for the snapshot, and changes are written to a new block. This ensures prior snapshots remain intact while current data reflects updates, balancing efficiency with data integrity. Accessing snapshot data is straightforward. Files reside under a hidden snapshot subdirectory within the original path e.g. /dir/snapshot/snapshot-name/file.txt. Administrators can list all snapshotable directories via HDFS ls snapshotable dia. To delete a specific snapshot, use HDFS dfs delete snapshot/path snapshot name, which removes the snapshot's metadata and reclaims storage for blocks no longer referenced by any snapshot. Crucially, deleting snapshots does not affect active files or other snapshots, as storage is freed only when all snapshots relinquish ownership of a block. Several factors warrant attention when using HDFS data protection features. The trash mechanism relies on user discipline. Accidental deletions require manual restoration before the retention period expires. Once trash purges files, blocks become irrecoverable. Snapshots, while powerful, are disabled by default and must be explicitly enabled per directory. Performance impacts from snapshots are minimal due to COW efficiency, but storage consumption grows proportionally with data changes post-snapshot. Thus, monitoring snapshot storage and setting retention policies are essential to avoid unchecked growth. To maximize data safety, adopt a layout strategy. Enable trash with a retention interval, e.g., fs.trash.interval equals 1440 minutes for 24 hours for non-ephemeral data, ensuring recovery windows for routine errors. Implement snapshots for mission-critical directories, e.g., /prod/finance, scheduling regular captures, e.g., hourly/daily to minimize data loss. Combine both features, trash for short-term undue and snapshots for long-term recovery, to create comprehensive protection against human error, corruption, or malicious activity. This approach balances operational simplicity with robust data resilience. File deletion flow. A deletion request moves the file to trash after the retention interval. Metadata is purged from the name node, and blocks are free on data nodes during heartbeats. Snapshots EOW. When file is modified after a snapshot, e.g., phone, HDFS preserves the original block for phone and writes changes to a new block file A. This ensures snapshot integrity while allowing live data updates. Visually, this resembles branching. Snapshots anchor historical states, while active data evolves independently with minimal storage duplication. HDFS provides two complementary data protection layers: trash for reversible short-term deletes configurable via fs.trash.interval, and snapshots for zero overhead point-in-time recovery. While trash acts as a user-centric safety net, snapshots offer administrator control versioning for critical datasets. Strategically enabling both trash for ephemeral data grace periods and snapshots for auditing/backup creates a resilient framework against data loss. Administrators should validate configurations, e.g., snapshot enablement, trash intervals, and educate users on recovery workflows to maximize system reliability.